Hello, this video is about waves. One thing to clarify is that in the F equals ma exam, wave behavior is not tested. Instead, an equation called the wave equation will be present in the F equals ma exam. Now, let's say psi is the variable for the wave equation, where the height of this wave equals to psi, and psi is a function of position and time. If I take an infinitesimal segment of this wave, then on the left-hand side, the tension force is going to apply at an angle theta. And on the right-hand side, the tension force is going to be applied at angle theta plus d theta. Applying Newton's law, the summation of the force along the x direction equals to t times cosine of theta plus d theta minus t times cosine of theta. Now remember that cosine of theta is approximated as 1 in Taylor series, and therefore the summation of the force in the x direction is roughly t minus t, which equals to 0. This is why in wave, the wave particle isn't actually moving horizontally, but instead they're just oscillating up and down in vertical motion. The summation of the force in the y direction equals to t times sine of theta plus d theta minus t of sine theta. And using Taylor series, this can be approximated as t of theta plus d theta minus t of theta, t times theta, because sine of theta can be approximated as theta. And if I subtract this simply becomes t times d theta. Let the variable mu be the mass length density, or just simply mass divided by the length. Then t times d theta, which this equals to force, equals to mu times dx, which is mass, times the second derivative of psi with respect to t. In this case, it will be the acceleration, since psi was the height in the vertical direction. Now, one thing to note is that the second time derivative of psi here has this weird derivative sign. Previously, the derivative that we're used to is called the complete derivative, and since psi is a both function of x and t, in a complete time derivative, x varies with time. However, in this weird notation, this is called a partial derivative. And in a partial derivative, x is constant. And it is very important that x is constant because when this wave oscillates, this object or this segment of the wave isn't moving horizontally, and therefore the position of this wave particle must be the same. Dividing each term by dx, this becomes t d theta dx equals to mu times second partial derivative of psi with respect to t. Now, sine theta was approximated as theta, and cosine theta was approximated as 1. Therefore, tangent theta, which equals to sine over cosine, is also approximated as theta, which means d theta dx equals to the derivative of tangent theta, and in this case, tangent theta equals to the slope, or this equals to the derivative of partial derivative with respect to x, because we're assuming that time is constant. Therefore, d theta dx equals to partial second derivative with respect to position. Plugging this value to the equation, I get tension times d2 psi over dx squared equals to mu times d2 psi over dt squared. And this equation is called the wave equation. But this equation exists at a different form as well. And the other form is d2 psi dx squared equals to 1 over v squared times d2 psi dt squared. And in this case, v equals to the velocity of the wave, and this velocity of the wave equals to the square root of tension divided by mu. And it is very important to remember the form of the velocity of the wave as well. So I've prepared some questions on the F equals ma exam related on waves. And first question is 2015 F equals ma, question 24. In this question, there are two strings, one with radius r1 and the other with radius r2, where r2 is 4 times greater than r1. Then, if these two strings are held at maximum tension, the question is asking what would be the ratio of the frequency of the first and the second string. Note that frequency is proportional to the velocity of the wave, because if the wave is traveling faster, then the wave is going to oscillate at a faster frequency. And remember that velocity of a wave equals the square root of the tension divided by the mass length density, or which is square root of T divided by m over L. Now, the force of tension is proportional to the cross-sectional area, and this is because a thicker string is going to have a stronger tension, and the measure of thickness of a string would be the cross-sectional area. Mass is going to be proportional to the volume, in which volume of a string equals the cross-sectional area times length. And this is because mass is simply the mass volume density times volume. Therefore, velocity of the wave, which equals the square root of T over m over L, is going to be proportional to square root of area over area times length divided by length, because tension is proportional to area and mass is proportional to area times length. Canceling out the A's and the L, this simply becomes 1. And therefore, this concludes that V is independent of R. And therefore, F1 and F2 must be the same, and therefore, the ratio of those two frequencies equals to 1. Looking at the option A would be the correct answer. The following question is 2017 F equals ma question 23. In this problem, there is a string where the equilibrium length equals to 1 meter. And if this string is stretched to a distance 10 meter and a wave pulse has been sent, the time it takes for the wave to arrive at one endpoint to the other equals to 1 second. This means that velocity, which equals to length over time, equals to 10 meter per second. Remember that velocity equals to force divided by mass length density, in which expanding this equals to force over m over L. Since mass of the spring is constant and force applied is force of the spring, from Hooke's law, this value is proportional to square root of change in length times length. But note that the equilibrium length is only 1 meter, while the stretched length equals to 10 meter. This means change in length is approximately same as the original length, and therefore we can claim that the velocity is roughly proportional to the length of the string. But since time for the wave to arrive from one point to another equals the length of the spring divided by the velocity of the wave, and the velocity of the wave is proportional to length, the time it takes is going to be constant. And in this case, it's just going to be 1 second. And therefore, looking at the answer, I'm going to choose C. The last question is from 2018 B F equals ma, question 11. In this question, there is a circular rope that is rotating at some angular speed omega. And if a wave pulse is sent, then the velocity of that wave pulse is equal to the tension force divided by the mass length density. But note that the mass length density of this rope is constant, because mass of this rope is going to be constant, and the rope is going to maintain the same configuration, which means the total length, which equals to 2 pi r, is also constant. Therefore, velocity is going to be proportional to square root of tension. Note that tension will be proportional to the centripetal force because only tension is present, which means the radial component of tension must be centripetal force. This means those two forces must be proportional to each other. Now, Fc from its definition equals to mv squared over r, but since v equals to r omega, this equals to m times r times omega squared. Again, since mass and r are constant, we can conclude that tension is proportional to angular frequency squared. Combining these two relations, velocity is going to be proportional to omega. And therefore, if the angular velocity of the rope is doubled, then the velocity of the wave pulse is also going to be doubled.